Hi, hello students. Welcome back to India's most comprehensive online learning platform, BYJU'S Exam Prep. This is Aneel Prasad Sir, and in this session, we are going to discuss about yet another important topic in the entire operating system, that is multi-processor scheduling. But before which, we'll also understand what is multi-level queue scheduling. And in this session, completely we're going to discuss about the two things. One is multi-process scheduling, in addition to which we also are going to cover multi-level queue scheduling. So let us start. Before we proceed, before we go any further, I request you people to like and share the session and subscribe to this channel if you haven't already yet. So let us get into the details. This is my experience and you already knew about it. This is my Telegram channel, and most of you people, they're asking, and yesterday when I was looking at the comments, some people, they're asking for my Telegram channel, and just look at this. I mean, just if you want to follow, you just can follow. And when you follow, whenever you have doubts, immediately shared within the channel itself. So let me take you people into the concept straight away. And we do have a session upcoming at 19th June 2022 at 12:30 p.m. That is How to Ace GATE 2023 by D.V. Sridhar Sir. Don't miss the session. Don't miss this opportunity. Follow this session and capitalize on the session. So let us start. So let me see. Let me check. All of you, your attendance. May I have you people? Hi Chitra, very good evening. And where are the other guys? Yeah, so let us start. Now, first of all, before I take you people into the concept of multi-process scheduling, first of all, we will understand what is multi-level queue scheduling. We know that we do have a main memory. Yes or no? We do have a main memory. What is main memory? Main memory itself is a ready queue. Every time when one process wants to execute, that process must be brought into the main memory, right? For several times, no matter for how many times we discuss, this is not gonna change. This will never change. Every time if you are a process, if you want to execute, you need to come into the ready queue. What is ready queue? Ready queue is just nothing but main memory, right? So the thing is, I mean, generally any processor, whenever we have a single processor, every processor will be associated with one only single main memory. And whenever there are a few processes, there are several processes in the main memory, we need to follow some scheduling algorithms in order to schedule the next process which gets into the CPU, right? Harshita, hi Krishna, hi Chitra, very good evening once again. Very good evening one and all. Focus and understand the concept carefully, understand the class, understand the session carefully, follow the session very carefully. Only the thing, the prerequisite that I expect from you guys is just take a scribble pad and scribble whenever you feel it necessary. Until you just need to focus on me, just need to understand the session. That's it. I don't expect anything from you guys other than this. So let us start. Let us talk about a multi-level queue scheduling. Let us say I do have a main memory, of course, any processor will be supported with a main memory on its motherboard. When it comes to the main memory, of course, in a multi-programmed environment, either in your desktop or in my desktop or in your mobile or in my mobile or a laptop, we are going to have simultaneously processes loaded, several processes loaded at this point of period. Let us say, in the main memory, I do have several processes. Let us say there is P1, there is P2, there is P3, and there is Pn. Several processes are loaded within the main memory. Whenever there is more than one process within the main memory, obviously we require to have a scheduler. Scheduler's job is to schedule the next process. That's it. Several times we discussed, I'm not taking this anymore. Already we knew this, right? Let us understand. Sometimes what may happen is, in any computer system, all the processes, all the programs can easily be classified into separate categories. I mean, they can get classified into separate groups based on its type, based on its kind, based on several factors. Any process can be, classified into some category. For instance, I will give you one example. Very good evening, Chanchal. Yeah, I'll give you one example. Example is, let us say, in either in your system or in my system, we do have two different kinds of processes. What are those? One set of processes can be called as the foreground processes, Another kind of a process will be categorized as background processes. What is a background process? What is a foreground process? If I may ask, can I ask what is the background process? What is the foreground process? What are the examples? Can I ask you people? Chanchal, can I get the answer? Chitra, Krishna, Harshita, Anu, can I get this answer? What is a foreground process and what is a background process? And if you can give me the examples also, that is more than sufficient for me. Yeah. What is a foreground process and what is a background process? I'm waiting. I'm awaiting your answer. I just want to know what is a foreground and what is a background process. Fine, I can't wait for more time. Let me tell you what is a foreground process. A foreground process is a process which requires the user's attention, user's interaction. For instance, MS Word. Any word processing application requires user's interaction. Without user's interaction, that application wouldn't execute. Similarly, when it comes to some other processes, some process doesn't require user's attention. They can run in background. Let us say some system update is happening. System update doesn't require any user's attention, right? Whenever Android system is getting updated, it doesn't require user's interaction at all. It can update background. Did I make it myself clear? So, upgradation, rather updation, whatever you call, it is still a process. When that process is running, it can run background. And when it comes to the MS Word or any word processing application or any VLC media player or any media player or any other application which requires users interaction can be considered as, will be classified as foreground processes. Here, we can understand, if you think sensible, the response time requirement is different. Background process doesn't need much response time requirement, but when it comes to the foreground process response time requirement is stipulated. Response time for the foreground process is very, very minimal indeed. Within no time, that process expects the response from the user. I hope it is making some sense. Here the thing is, foreground processes can be given priority over the background process. Now let us talk about a multi-level queue. What exactly is this multi-level queue? Let me explain. That is, let us say, if you are able to classify the process into separate groups, the same main memory, which is called as a ready queue, can be divided into separate queues. Okay, now, initially, my main memory is just divided into, at this point, as we discussed about a foreground process and background process, two different ready queues. I would say RQ1 and RQ2. Okay, this ready queue 1 is going to accommodate all the foreground processes, and this ready queue 2 is going to accommodate all the background processes. The thing is, foreground process will have the priority of the background process. Here I do have two different ready queues. System has two separate ready queues. Here, how to go for the scheduling? What are the frameworks for the scheduling? How the processes needed to be scheduled? Here the thing is, there are several things needed to be considered. This is a challenge for a designer. Whenever we do have more than one ready queue, depending on the type of the processes, there are several challenges for a designer to schedule the processes. Here, the processes can be scheduled by its queue itself. Every queue will have a priority. Right after a priority is assigned, the process within the queue will get executed. Of course, obviously, ready queue 1 has foreground processes, will have priority 1, right? This got the highest priority. Second one is ready queue 2, which has got the background processes, will have priority 2. I hope it is making every sense. Background process doesn't require the user's interaction, hence it can be given lower priority. But foreground process always need to execute, as well as it needs also the user's interaction. So priority 1, foreground process, ready queue 1, priority 2, ready queue 2, background processes. Here the thing is, obviously we expect all the process within the ready queue 1 to be finished. And right after which, we schedule the other process which are in the ready queue 2, which are called as a background process, can be executed since it is given with the lowest priority. Here the thing is, which scheduling algorithm to be followed, which is the best scheduling algorithm. There is no specific scheduling algorithm you can follow. Each ready queue can have its own scheduling algorithm. For an instance, for the priority one, for the ready queue one, you can use SJF. For the ready queue 2, you can go for what we call round robin. If you do have more than one ready queue, each queue can have its own scheduling algorithm, depending on the scheduling requirement of the processes. Whenever a process is assigned to a queue, based on the factors and parameters, each and every process, rather each and every queue will have its own scheduling needs. So every queue can have its own scheduling algorithm followed. I hope you got the point. Foreground process needs user intervention. Absolutely. User intervention is required for foreground process, for all the foreground processes. This is what multi-level queue scheduling initially and to begin with. But understand something. The multi-level queue scheduling, in the initial state, what we have defined is, we define two queues initially, Q1 and Q2. This is foreground and this is background. I already told you foreground will have priority 1, background will have priority 2. The thing is, until and unless all the processes in the foreground queue gets executed, there is no ever way for any background process to execute. Here we may have something called starvation. All the processes within the background may starve for the CPU scheduling. No ever process in the background queue can ever get scheduled until and unless all the process gets finished in the foreground queue. Here, in order to avoid the starvation, what exactly we can do is, we can time frame foreground process and background process. In the entire availability of the CPU time, we can give foreground process much time and the background process somewhat lesser time. For instance, foreground processes can be given, the foreground queue can be given with 80% of the total CPU time, and the remaining 20% can be assigned to the background process. So, in every 100% of the clock cycles, for 80% of the clock cycles, foreground process will get executed. So, in order to avoid the starvation, right after 80% is finished, foreground process cannot execute anymore. Remaining 20% should strictly be given to the background processes. So, likewise, we will be able to avoid starvation. This is exactly what all about multi-level queue scheduling. But there are several parameters to be considered, several factors to be considered whenever we are going for multi-level queue scheduling. Understand those very carefully right now. The ready queue consists of multiple queues. Multi-level queue scheduler defined by the following parameters: number of queues, scheduling algorithm for each queue, method used to determine which queue a process will enter when that process needs service, scheduling among the queues. The thing is, how multi-level queue scheduler will be defined? The thing is, first of all, how many queues we can have the system. Number of queues depends on what factor? The categories of the processes, right? How many categories, how many types of the process we do have? I do have a total of 5 different types of the processes. Simple. I can have 5 ready queues for each type of process, for each category of the process. We can have 1 ready queue. I do have only 2 types of process, 2 categories of the process. So, the number of queues will just be equal to 2. Then, scheduling algorithms for each queue. Next thing is, you need to examine, you need to analyze each queue. What is the kind of a process available there? What are the different kinds of process available there? As altogether, they are of a specific kind, they may request for a scheduling algorithm. They may need of having a specific scheduling algorithm implemented. For that, you need to take a call. Which scheduling algorithm to be stitched to which category, which queue of the processes. Each and as I told you already, once again, let me admit firmly that each and every queue can have its own scheduling algorithm depending on the type of the process that it contains. And then method used to determine which queue a process will enter when that process needs service. Obviously, every process during the execution it may require a kernel service, right? Obviously, when a kernel service is needed by any process, it enters into the kernel mode. The moment a process enters into the kernel mode, actually to which queue you are going to send it. It is one more decision, one more parameter that is needed to be considered very, very carefully. All these parameters you should be able to consider and taken care of. Next, scheduling among the queues. How you are going to schedule among the queues? There are two things to be taken care of. The first thing, scheduling within the processes of each and every queue. Right after which, we should also take care that how we are going to schedule the queues. Which queue will be given the highest priority? Which queue will be given the next highest priority? What is the time stamping? And the available 100% of the CPU time, how you are going to distribute this time? All these things should be considered, should be taken into consideration, and the parameters that are need to be considered so far, I've just discussed. Right? Now, this is very simple, as I told you. Only the thing is, we should be able to classify the process and attach them to each queue. Here the thing is, in a multi-level queue environment, the moment when a process comes into the system, it will be assigned to a fixed queue, as I show you right now. With priority scheduling, have separate queues for each priority. For each priority, we do have a separate queue. Rather, for each queue, we do have a separate priority. Of course, obviously, schedule the processes with the highest priority queue. The process which are in the queue, which has got the highest priority, will be scheduled prior to the other processes which are waiting in the next queues with a lower priority. Okay, I mean, let us say this is a queue with the highest priority, next highest priority, next highest priority, next highest priority. Obviously, T0, T1, T2, T3, T4 will execute prior to T5, T6, T7. Since second queue has got first priority, of course, considering its priority 0, obviously it is smaller than 1. Obviously, the first queue will be given the highest priority. Until and unless T0 to T4 are executed, there is no way that I can execute T5, T6, T7. Similarly, unless T5, T6, T7 gets executed completely, I can't execute T8, T9, T10, T11 waiting in the second queue. Similarly, every queue is a subsequent queue to its predecessor, right? So here in this way you need to take a call. Which should be given the highest priority, which should be given the least priority. Now here you can see the system with 4 queues. Real-time processes, system process, interactive process, and batch processes. Obviously, as we discussed earlier, a real-time process should be given the first priority, right? Right after yesterday's class, I would not want you people to have any confusion in this at all. Real-time process should be executed initially at the instant it arrives into the CPU. Yes or no? Krishna or Anu or Chanchal, Anu, you there? Chitra, you there? Answer this. Do I have any more process executing while a real-time process makes its way into the system? It's not possible, right? Yes or no? Answer. Chitra, answer. Anu, answer. The moment a real-time process enters into the system, can we execute any other process in the system? No. Real-time process has a strict constraint to execute within a stipulated time limit. Did I make it myself clear or not? I hope I did. Yes. I mean, obviously, real-time process will get the highest priority, followed by system processes, followed by interactive process, followed by batch processes. I mean, these batch processes are not interactive. What is a batch process? Batch processes are the set of processes that can be submitted to the CPU and they can execute any time. What is a batch process? Batch process will be collectively sent to the main memory. Batch processes they doesn't require any user's intervention at all. User's interaction is not required. With the batch process, obviously you can see a real-time process will get the highest priority. The moment a real-time process enters into the system, it will be classified as a real-time process and it will be sent into the queue of the real-time processes. Next, The moment a system process comes into, immediately it will be assigned to the next one. Similarly, interactive process will be assigned to the third queue. And similarly, when the batch process enters into the system, it will be assigned it to, the fourth queue, what we just have discussed. Here the thing is, in the multi-level queue, the moment a process arrives into the system, it will be assigned to a fixed queue. And it cannot move from one queue to another queue. Based on this type, based on its kind, we are going to allot one queue to it. Immediately it will go and sit within the queue and it will await to get into the CPU. As simple as this. But the thing is, assigning a fixed queue to any process can lead to several complications. For an instance, I will give you one simple example. I am process PNI. The moment I made my way into the system, I got sent to interactive processes. So my priority is 3. Okay, rather my queue's priority is 3. In which, according to the scheduling algorithm, let us say interactive process, for this queue, we are following SJF. For this system process, the operating system is following what we call RR. Here this is priority based. Obviously, when it comes to real-time processes, obviously we need to use priority based algorithm, that is earliest deadline first scheduling algorithm. Earliest deadline first. Batch processes, they can execute as they want. I can follow FIFO for batch processes. Now, these are the scheduling algorithms that are used in each of the queue. The moment Aneel enters into the system, he got sent to interactive processes. But the thing is, sooner or later, this PNANI needs to execute within a kernel. He needs a system service. For instance, when I require a system service, what is going to happen? Immediately, I will execute in the kernel mode, right? When I execute in the kernel mode, I may update some important kernel data structure. At that time, my priority should be increased. Simple. But the moment I enter, I cannot do anything. I will be assigned to a fixed priority queue. Rather, my priority will always be fixed, and my queue's priority also is fixed. I can't do anything. But this fixed priority business is going to lead to a lot of complications, as I told you. So what we need to do is, we need to update the concept of the multi-level queue scheduling to multi-level feedback queue scheduling, in which the process can move from one queue to another queue. The process can be allowed to move from one queue to another queue. I hope I made it myself very clear. Hi Divya. Hi Harshita. I think Harshita, you just made your way. Of course, you already there. Batch of jobs needed, yes. And Chitra, I'm not getting the answers. Yes, foreground process needs user intervention. Let me have a look at your comments, and each queue may follow the different algorithms. Of course, Krishna, you're spot on. Lower priority process may start. I told you how the starvation can be avoided. See, I will tell you something. Starvation can never be anticipated, can never be, entertained in any operating system. If there is a starvation, we need to take some fixed, set of protocols to avoid the starvation. Every operating system, no matter which operating system you are using, no matter which operating system we are following, needs to take necessary steps to avoid the starvation. Aging is one of the, important methods to avoid starvation. For instance, I will give you one wonderful example for how to avoid starvation. Let us take an example of Indian Railways. The best railways in the world. I can't say anything. Of course, Indian Railways are the best railways in the world. Don't laugh. Of course, it is the best railways in the world. Let me admit firmly. Okay, fine. Let us say, I boarded a train. My train is, let us say from Hyderabad. When I want to go to some place, I will catch some train. From Hyderabad, my city of origin, I just want to go to Bangalore. At that time, I may, board an intercity express. But there comes Rajdhani Express. Rajdhani Express has got a higher priority. Now, obviously, what will happen? Immediately, my train will be sent to the loop line. My train will have to wait that Rajdhani train to pass. But followed by some Duranto. Duronto has to pass. Meanwhile, while the highest prioritized trains are going off, I mean, as long as they are going off, my train cannot run, right? But the thing is, if you keep, lower prioritized train on the loop line, when it will start, obviously, for lower prioritized train also, there is a time. Even if it is delayed by one, what do you call, 1 hour, 2 hours, or 3 hours, or 4 hours, finally it needs to reach its destination, right? In my childhood days, it used to happen that, I heard the things like a train is running by more than 36 hours late. But right now, it is pretty much limited. The delay time is pretty much limited. And now, how the starvation can be avoided? My train, which is traveling from Hyderabad to Bangalore, how can we avoid the starvation? Simple. If I spend for some time within the loop line, my priority will get increased. No matter what. If I wait for 5 minutes, priority will get increased. Wait for 5 more minutes, priority will get increased. Right after some certain point of period, Indian Railways doesn't afford this train to be on the loop line. Immediately it will be brought back to the main line. It will have to pass by. No matter at that time, the moment it attained the priority, highest priority, even if the Duronto comes, it cannot be stopped. Duronto has to be in the loop line. I hope you got it. Here, fine. This is called aging. Any process. Now we will apply the same concept into operating system. Operating system does exactly to avoid starvation. The moment a process comes in, there will be a timer associated. Every time the timer is ticking. For every 24 ticks, the priority 1.001, I forgot the protocols of what you call the window scheduling. Window scheduling, of course, 24 ticks, I guess so. But I will come up with the exact, total things. But right now, for every tick, for every 24 ticks, let us say for an example, 0.001 priority will get increased. Sooner or later, as that is progressing, definitely this process will, after some time, which entered initially with the least priority, will attain the highest priority, right? This is how we are going to avoid the starvation. Similarly, here also, in multi-level queue scheduling, how we avoided starvation, we time-stamped each and every queue. Let me tell you, here we have 4 queues, right? Each of these queues will get time-stamped. Okay, here the thing is, real-time process, the first one will be given a timestamp of 40. I'll give 50% because real-time process, a real-time process, we already understood yesterday. We already almost went to the heaven and about to sit next to our grandparents. We would, better avoid that scenario. Everybody would prefer avoiding the scenario. So 50% will be given to real-time processes. Next, system process may be given 20%. And interactive processes may be given 20 more percent, and the batch processes will be given 10%. So likewise, we'll be able to still avoid the starvation. Did I make myself clear, or is it making sense? You're listening or not? I just please, make you mark here. Divya, Krishna, where are you guys, sir? Batch, Anu, where are you, Krishna? Where are you, Divya? Where are you, Chitra? I want you people to participate. I just do not want to teach, to the set of walls and to this scam. I want to teach you people who are sitting just right next to the systems, right in front of the systems. I want you people to participate. Here, I'm not in a class. I don't know whether, unless you communicate, I don't know what exactly you're getting. Yes, obviously. Yes, true. Okay then. So this is a real-time process and batch process. Can I go to the next slide? You got everything so far? Can we get into multi-level feedback queue scheduling? Right after which, let me tell you, I am going to take you people to another complex topic to be made simple by myself. Unless you say yes, I don't take you people to there, multi-process scheduling. Okay, so I need you people to say yes here. Multi-level queue scheduling. A process can move between the various queues. Multi-level feedback queue scheduling. Let me take you people into. A process can move between the various queues. That is, in the previous case, we had already seen a problem. if a process is assigned to a fixed queue, I mean, that is imposing several restrictions, several constraints. So we just want to update to multi-level feedback queue scheduling. So what we do is, we will update this to multi-level queue, to feedback queue scheduling. What am I saying? Earlier we were talking about multi-level queue scheduling. Now we are updating to multi-level feedback queue scheduling. This is correct. Yeah. Within multi-level feedback queue scheduling, stay careful. A process can move in between the various queues. During its lifetime, a process can move from a lower prioritized queue to the higher prioritized queue, or it may get demoted to a lower prioritized queue from a higher prioritized queue. Okay. A multi-level feedback queue scheduler defined by the following parameters. Simple. If you want to define multi-level feedback queue scheduling, first of all, you identify the categories of the processes within a system, which defines your number of queues. Next, scheduling algorithms for each queue. I defined this precisely, right? Next thing is method used to determine when to upgrade a process. Okay, and followed by method used to determine when to demote a process. Yeah, very good. I mean, seeing you people smiling, of course, it made my day. But hold your horses and just follow the session. But keep on smiling. You know what? Smiling is the feature that is only attributed to the human being. Only human being can smile. No other animal, no other species can smile. And no matter what, no matter in which situation we are, we should always smile. I mean, that should be applicable to every human being. As long as we smile, there are no, nothing can go wrong. Only the problem is, people started forgetting smile. I mean, they are getting carried away by the flow of their work or by the flow of their day-to-day routines. You do not fall into the trap of day-to-day routines. Keep smiling right from the day, right from the time you wake up till the time you go to bed. You keep on smiling. That will make your day, including the others' day. So this is my humble request. So let me take you people back to multi-level feedback queue scheduling. Method used to determine when to upgrade a process. Method used to determine when to demote a process. Method used to determine which queue a process will enter when that process needs service. Okay. Aging I talked about, I guess. I hope you completely got yourself with, well versed with the aging. Now, I will take a simple example about this multi-level feedback queue scheduling. Now let me tell you. In order to take an example, I will take a simplest example. The example is, I will just take only 3 queues. This is the first queue. Did I make it myself clear? Are you with me? Stay focused. Let us say there is first queue, there is second queue, and there is third queue. Okay. The thing is, the moment a process enters into the system, here once again, this will get the highest priority. This got the first priority. This got the second priority. This got the third priority. Okay. Now the thing is, obviously, the moment a process enters into the system, obviously it will be given to the first queue. It will be assigned to the first queue, no matter to which type you belong. You will be assigned to, no matter it's you Anu or Chitra or Chanchal or Krishna, no matter who you are, you will be sent to the first queue. Okay. Here the thing is, let us analyze the first queue. The first queue is assigned with a time quantum of 8 milliseconds. That means, being a process, you will be given with a span of 8 milliseconds to execute within a CPU. Everybody, this is uniform for all the processes within the first queue. Every time when a process enters, it will be assigned to the first queue, and that process, including all the other processes, will only be given 8 milliseconds. So obviously, every process from the first queue will be given to the CPU. The moment it executes, if it finishes within 8 milliseconds, it will leave the system. If it exceeds 8 milliseconds, immediately it will be preempted out of the CPU and will be appended as a tail to the second queue. It will be appended as a tail to the second queue. Now understand, right after all the process got executed, we got only those processes which would take more than 8 milliseconds left in the system. Yes or no? Once again, in the simple words, the process which enters into the system, all the processes finished, which can take which would take less than 8 milliseconds. The process which would take more than 8 milliseconds, still they are left within the system and they are available in the second queue. Okay. Now, within the second queue, the time quantum has been increased. Here, time quantum is 16 milliseconds. Round robin with a 16 milliseconds. Every process will enter into the CPU, can only use 16 millisecond share. Right after which, if you can get executed well and before 16 milliseconds, it is well and good, you will leave the system by yourself. Otherwise, what I'll do, I will pull you back. No matter, what's your priority. Even if you're a minister, I don't mind. I will pull you back. I will keep you in the third queue, which is following a scheduling algorithm, that is FCFS. So right after second queue, all the process within the second queue finished. The process which can execute within 24 milliseconds are already done with the system. 16 plus 8 is equal to 24. The process which would take less than 24 seconds already left the system. The process which would require more than 24 milliseconds of time of the CPU are still left with the system. Left in the system, they are appended to the FCFS, the third queue. In the third queue, if you actually can think sensibly, only the longest process remaining in the system, right? The process that are available within the system are the longest process. Any process which would take more than 24 milliseconds is the longest process ever, right? So obviously system only is left with FCFS, rather longest process. Let them execute any time they want. I hope I made it myself clear. Yes or no? Obviously. No, smiling doesn't increase only your lifetime. It increases everybody's lifetime, right? Okay, early in the morning you just watch a newspaper. Newspaper itself, it's a chaos. The moment you look at your newspaper, of course, your total day will be made miserable. So, when you watch a cartoon, Tom and Jerry, immediately you start smiling. That will make your life as well as the other people's life very, very comfortable indeed. Yes or no? Yeah, fine. 3 queues. Round robin time with a quantum of 8 milliseconds. Round robin time quantum with 16 milliseconds. And finally, it is FCFS, as I told you. Scheduling. A new process enters into a system will be assigned with a Q0. When it gains CPU, the process will receive only 8 milliseconds of CPU time. If it executes, well and good. Otherwise, it will be printed and appended back as a tail to the second queue. And the third one is, if Q1 job is again served in RR and receives 16 additional milliseconds, this time it's got 16 additional milliseconds. If it still doesn't finish its execution, it will be printed back and appended as a tail back to the third queue, in which only the longest process remaining in the system, no matter how they execute. So what we do is, let them execute anytime they want, so you just assign FCFS. Okay. Now, let me take you people to the concept of multiprocessor scheduling. Okay. It is, of course, again, let me take the help of my computer architecture. Let me bring the computer architecture and blend it with the operating system to completely understand this topic. Let us recall. Shall we get into the multiprocessor scheduling? Yes or no? Can I? Very nice to see. Very, it's been phenomenal to know this. Very good, Anita. Very good. Yeah. Now, can we get into multiprocess scheduling? Now, let us understand. Multiprocess scheduling. What are the challenges that we're going to face with multiprocess scheduling? Understand carefully. What is a multiprocess system? The computer system with more than one processor. Alright? When there is more than one processor, it will be called as a multiprocess system. There are several types of multiprocess systems. Basically two. We will call it as symmetric multiprocessors and asymmetric multiprocessors. SMP, ASMP. Symmetric multiprocessors and asymmetric multiprocessors. So think simple. You don't need to even write anything at all. Just keep your pen there and close your book. Just listen to me. I'm going to make this concept very simple within no time. Okay. What is SMP, ASMP? In the asymmetric multiprocessors, there will be a server and there are a few clients. Server is the boss. Clients are just the peers. Clients have to listen to server. Here, when it comes to the ASMP, server will take the load of everything, including scheduling. Let us say we all together we form a multiprocessor. I am the server, you people are the clients. You got nothing to do. Just what the option you got, kiddos? Only the thing is just need to listen to me. Because I am the server here. When I ask you to do something, you just need to do the thing what I ask you people to do. But when it comes to SMP, things will be different. What is SMP? In the symmetric multiprocess systems, all the processes are independent and individual. At that time, there is no server. Here, every processor needs to look at its scheduling needs. It needs to self-schedule. So, let us understand. Here, we don't need to talk about ASMP since as the server can take care of everything. But when it comes to the SMP architectures, things would be completely different. How? In the SMP architecture, all are peers. Okay, all are clients only. I mean, we can't even say clients, all are individual and independent. Here, let us talk about SMP. In SMP, there are again different challenges for scheduling. Each and every processor should take care of its own scheduling. But now let us have a look at. There are two kinds of SMP architectures. One with a common ready queue, with a common main memory. All the CPUs are connected to the common main memory. Okay. Otherwise, the different SMP architecture is with the different ready queues with the different main memories. Okay. Now, let us understand the challenge with the first case. The CPUs with a common main memory. Okay. Understand carefully. Every processor, I would say XYZ. Processor A, processor B, processor C, processor D, processor E, has to self-schedule. Now there are several processes, P1, P2, P3, and P4, P5. Let us say currently all the processors are running and executing some processes. Got me? Now the thing is, stay focused. Let us say, two processors, B and E, exactly finish their process execution within the same time. Not even by a quite margin. Exactly at the, precise millisecond. These B and E finished with their execution. Now, B and E needs to select next process, right? Here already you can see, this B and E can select only one process. Same process, right? There is every chance for B and E to select the same process to execute next. This is the biggest problem. When a single process is selected by more than one processor, what exactly is going to happen? Rather than being scheduled to at least one processor, this process may leave the system, may be suspended from the system, may be completely terminated from the system. This is a problem. Yes or no? Is it making sense or not? The thing is, let us say B and E finish with their process's execution at the very moment. At the time, right at the very next clock cycle, they need to select the next process from the main memory. As it is a single main memory, single ready queue, all the process will be waiting to get scheduled to one of the processor. There is every chance for this B and E processor to select the single process from the main memory. At that time, rather than getting scheduled to at least one of these processors, this process may completely be out of the system, out of the context. This is the first challenge that is needed to be faced. Operating system needs to avoid this and needs to take necessary precautions to avoid this. Okay. Now let us understand the other challenge, which is more catastrophic indeed. I will tell you. Let me, several processors and the main memory. Here, the main memory is divided. We don't have a single ready queue. We do have different ready queues. Let us understand. When we do have different ready queues, there will be one more problem. This problem is even more catastrophic than the previous problem what we discussed. What is this problem? Understand. In order to understand, please follow and please just listen to me carefully. You don't need to write anything. Let us say something. Let us say that the moment one process arrives into the system, it will be given randomly to one ready queue. Okay, this is for this processor. Every processor will have its own share of its ready queue. Okay, let us say there is process P1 got scheduled into A initially the moment it arrives into the system. When P1 gets executed into A, of course we expect P1 not to finish completely. Due to the scheduling algorithm's preemption, P1 may come out of the processor before its completion. When it comes out, what may happen? Understand, during the preemption, it may come out, or it may go to one IO operation, right? Whenever a process enters into the processor, sooner or later, it either get preempted or it may go to some IO operations, right? So let us say P1 went to IO operation, right after which obviously A will not be free. A is scheduled with one more processor, that is one more process, that is Px. Now understand. When P1 returns, to which ready queue it must be allotted? This is the biggest question. Yes or no? Are you staying? Anita, Harshita, and Divya, you people there or not? Anu, Chanchal. Yes or no? Now, when P1 comes back, to which ready queue it will get scheduled? The thing is, we expect the P1 when it returns back to be kept in the same ready queue as before, that is the Q1. But it is not guaranteed since ready queue may be already full. When the ready queue is already full, this P1 cannot be appended to the ready queue. At that time, P1 may be scheduled to one more ready queue. Let us say P1 comes here. This queue belongs to this processor. At this time, we are going to face a serious trouble. Let us understand. Are you with me? Stay focused here. When the processor, when process executes in any CPU for its first time, obviously this process's data will be available in the local cache of the processor, right? Every processor will be associated with a cache memory. Yes or no? Being a computer science guy, I would expect you people to know this silly little thing. If I am a processor, I will be having my local cache memory, right? Every processor will have its local cache, right? So, let us say when process P1 enters into A first time, obviously process P1's data is loaded within the cache memory of the processor A, right? The thing is, when P1 went to IO and comes back, if it is scheduled to some other processor, the thing is, this data must be loaded again into the local cache of this processor. Why we have cache memory? In order to compensate the speed differences between CPU and the main memory, to have the faster execution of the process, we require the cache memory. Now you can clearly see the usage of the cache memory straight away. The fundamental reason why we use the cache memory is straight away being at stake. We can't afford this. Whenever a process enters into the CPU for the first time, obviously its data will get loaded into the cache memory. But In the multiprocessor system, if it gets scheduled to some other processor after preemption, it will be catastrophic since data must be loaded within the local cache of that processor. What if it just went to IO for 100 times? Every time when it comes back, it has got scheduled into different processor. There is no point in cache memory at all. I hope I made it, very clear indeed. Yes or no? Scheduling complex in case of self-scheduling. Yes. Migration I'm not talking about. I'll talk about a migration. Okay. Now the thing is, we need to address this problem. This problem is called processor's affinity. Every process, when it enters into the CPU, for the first time, it will develop a bonding. That bonding is called affinity. Why I developed a bonding towards a processor in which I executed for the first time? Because my data is already with the processor. But at the time, if I got preempted back and I got sent to one more processor, before I enter, I should be able to explain to that processor, who am I? And what is my data? Because I need to load the cache memory, that specific cache memory again with my data, which consumes a lot of time. This problem is called processor's affinity. So we need to address this problem. This problem will be addressed in two different ways: soft affinity and hard affinity. What is soft affinity? What is hard affinity? Let me tell you. Soft affinity meaning, when a process comes back, it will be given the priority to be going back to the same queue over the other processes, but not guaranteed. What is soft affinity? Once again, I went to a processor X, Anil went to processor X initially, but right after which Anil went to some IO. Upon returning, Anil will be given the priority over the other processes, but not guaranteed. If for that, this queue must be free. If the queue is free, Anil can get back to the same queue again because he's given the priority. But if the queue is not free, you cannot do anything. But let us say about the hard affinity. In the hard affinity, every process, the moment it enters into the system, it will be assigned to a fixed set of processors. There can be n number of processors, right? But among which only a fixed set of processors can be allocated to every process. Let us say the moment process P, CHI gets into the system, the moment it enters into the system, it will be assigned with a fixed set of processors. What are those? It can either execute in processor P2 or processor P3 or processor P10. That's it. Initially, it will be given to processor P2. When it goes out and comes back, P2's ready queue will be checked for any vacancy. If there is no vacancy, P3 will be checked for any vacancy. If there is no vacancy, definitely P10 must be able to accommodate it in its ready queue. There is no other option. There is no other scope at all. Every process, when it enters into the system, right the moment it enters into the system, it will be assigned with a fixed set of processes. Rather than populating every cache, rather than loading my data in each and every cache, obviously 3 caches are far better, right? If I'm assigned to a fixed set of processors, it will resolve the problem. I hope you got the point, right? Yes. This way, let us say somebody proposed this solution, soft affinity and hard affinity. Hard affinity, of course, for me, it is the best solution. But let me tell you. Anu, just a short while ago, she talked about something. That is migration. I need to talk about the migration right now. Are you with me? See, operating system is not as simple as it is defined. When you look at the operating system appears as a beautiful concept since within no time we can get it. But I want you people to master every topic. Looking at at a distance, any topic can be look very simple. But I want you people to enter. At that time, it looks more beautiful as you are able to figure out everything. You are able to figure out the modules. And one more thing is, I want you people to go for the case study. Every time when I explain the operating system, I'm taking the concepts of Linux and Unix or Windows or Mac, right? I'm talking about APIs. We need to take a case study and then understand the perspectives of the modules of the operating system. Otherwise, operating system is just seen, any topic, not only operating system, will be seen from a distance. So, understand carefully. Here, we discussed that hard affinity is the solution, the best solution for the entire problem that we discussed right now. But there is some counteracting concept here. Okay, since total operating system cannot be developed by a single guy, I am dealing with this. Let us say I am dealing with this problem, with this cache problem, cache affinity problem. One of you guys, Mr. Chanchal or Miss Chanchal, dealing with one more problem. Chanchal's problem is that she is given with developing a module to solve one more problem. She has to solve, let me tell you, stay with me. CHAN. She has to solve one problem. What is that problem? Load balancing. What is load balancing? She needs to make sure that every processor's load is evenly distributed, equally distributed. Why we will have several processors? To exploit multiprocessor, we should be able to take care that each and every processor is sufficiently loaded. None of the processors should be overloaded, none of the other, the processor should be idle. In order to make sure that, this load balancing is being implemented by some guy, some software developer, the module developer. In order to provide a solution, he can find or she can find two options. One is push migration, second one is pull migration. What is push migration? In push migration, this, developer develops a process, writes a module of a process. This process duty is to execute periodically, and it will check the load of each and every processor. She created one guy, a process. Okay, this guy will execute periodically, and he will check the load of each and every processor. And if he finds out any inequalities, he is going to move the process from the overloaded processor and put them into the idle processor. So likewise, push migration can be implemented. In the push migration, one process will execute periodically, and it is going to get the process from the overloaded processor, and they can be put into the idle processor. Pull migration is one more solution for this. In order to have the load balanced equally, when it comes to the pull migration, when a processor becomes idle, he himself pull the processes from the other processors. Got me? I will see the moment I got idle, immediately I will look at the other processor. I will go to the ready queue, I will bring those processes, even though they are screaming, even though they are shouting, why I don't come, why they are screaming, why they are shouting, I will tell you. Okay, I got some processes, but they are screaming, I don't want to come to you, I cannot execute. Fine, doesn't matter, I am idle, you need to come to me. I just got them scheduled to me. Here, why the other processes are screaming? The other processes are screaming simply because the process affinity, right? They are in a queue for a purpose. Not by chance. They entered into a queue for a purpose. What is the purpose? Because they developed a bond to that processor. They had an affinity towards the processor. Now, this load balancing, either it is a push migration or pull migration, completely counteracting processor's affinity, whatever the solution that we have proposed, completely being counteracted by the load balancing itself, right? Now we need to fight. Being a modules developer, we need to fight. No, I need to satisfy my criteria. You will say, I need to satisfy my criteria. This is what the beauty of the operating system. When you want to provide a solution for a problem that is arising in one module, that may counteract another module's one more problem. So this is exactly how the operating system is to be developed. I hope you got the point. Yes or no? When a thread has been running on one processor, the cache contents of the processor stores the memory accessed by the thread. Of course, we refer to this as thread having an affinity to the processor. A thread or a process will develop a bond towards the processor in which it is executed for the first time. Load balancing may affect the processor's affinity, as a thread may be moved from one processor to another to balance the loads, and that thread loses the content what it had in the cache of the processor it was moved off, which is what we discuss. In the soft affinity, a process will be given the priority over the other processes whenever it is moving back to the same ready queue. But in the hard affinity, any time when a process enters into the system, it will be assigned with a fixed set of processors. Push migration, pull migration, I told you already. What is a push migration? A process will execute constantly to check if the load is even. If the load is uneven, it will make the load even by moving the process from one queue to another queue. Pull migration, a processor, when it becomes idle, it is going to get the process from the other queues. In either case, processor's affinity will get affected. Yes or no? Okay. In NUMA, we do have one more problem. What is NUMA? Non-uniform memory access. When you do have multiple processors, there will be multiple motherboards. In each and every motherboard, there is a memory unit. Now you can clearly see the CPU can access the main memory module which is attached to the same motherboard faster than it accessing the other memory unit. Okay. So this non-uniform memory access also imposes some restrictions, practical restrictions on scheduling. Whether a process to be scheduled to the same CPU as in the motherboard or to the other processors. If it has to be scheduled to the same CPU, there is no point in having multi-process at all. If it has to got scheduled to the other CPU, obviously it will take some time. So we need to understand that nothing is like very simple but yet complicated. We should be able to resolve all the problems as we stated in this session. I hope I made it very, very clear. Okay, so that's all about multi-process scheduling, the challenges that we need to face in the multi-process scheduling and multi-level queue scheduling. That's it from the session. Any doubts you have, you can post. Otherwise, Aneel Prasad Sir is about to sign off. Then fine, that's it from the session. Please like and share this session and subscribe to this channel if you haven't already yet. Okay, thank you so much. Aneel Prasad Sir signing off. Master slave scheduling, master will take care of. Okay, thank you so much.